All right, welcome everybody. So in this video, we are going to finally put into practice some of the tools that we've been practicing with orthogonal projections, finding orthogonal bases using the Gram-Schmidt process, finding orthonormal bases, and using these constructions to come up with best approximations. So let's consider an application where we could apply this. So let's imagine we would like to come up with a model that's going to predict how strong a country's economy is based on two different predictors, A1 and A2. So we're going to measure the country's economy. We're going to denote that Y. And one measurement of how strong a country's economy is would be their GDP, their gross domestic product, which is the amount of all of the goods that a country produces in a year. And because we often want to compare countries that have really large populations with countries that have smaller populations that are going to produce less, but that might not be a result of how advanced their economy is, we scale the gross domestic product per capita, meaning we'll divide this value by the population. And therefore, this gives us a way of comparing the production levels of countries that have very different population levels. So this is a very common metric for the strength of a country's economy. And let's imagine that we believe that this can be predicted by two variables. A1 is the literacy rate of a country's population as a percentage, and A2 is a second variable, which is how healthy a country is, and we'll measure that by the life expectancy of that country's population. So what I'd like to say is if I happen to know the literacy rate of a country and the life expectancy of a country, how can I use that information to predict what that country's wealth will be, what their GDP per capita will be? So typically we would collect a really large sample of data. In this case, just so that we can do these calculations by hand, we'll pick a sample, let's say, of 3 different countries. And these are 3 actual countries that I picked at random. So country 1, their values are being recorded in the top row. So this 98 means their value for A1 was 98. This country has a literacy rate of 98%. So 98% of that country is literate, and the life expectancy of that country is 78 years, and that country's GDP per capita is $13,000. Country 2 has a literacy rate of 81%, a life expectancy of 76 years, and their GDP per capita is 11,000. And country 3 has a literacy rate of 92%, a life expectancy of 72 years, and their GDP per capita is $8,000. And so based on this sample of 3 countries, I would like to come up with a model that says, given these 2 values, how can I predict the country's GDP per capita? And then we could apply this to countries where maybe we know their values for A1 and A2, but we don't know what their value is for Y. So we have set up all of the observed predictor values in this matrix A that we'll call the model matrix. So this has our values for A1 and A2. So A1 values, literacy rates are in the first column, and A2 values, the life expectancy is in column 2, and then we'll store the response values, which are the GDP per capita, in a separate vector Y, but the ordering here is important. So this value for Y corresponds to these 2 inputs. So this is country 1, this is country 2, and this is country 3. Okay, so now we have our observed values for a literacy rate of 3 different countries, life expectancy of 3 different countries, and their corresponding GDP per capita. And we would like to find a regression model that has the following form, that Y, GDP per capita, is equal to some constant beta 1 times the literacy rate of that country plus some other coefficient beta 2 times the life expectancy of that country. And this is going to be the error term of that estimate. So this first piece over here is going to give us our prediction. And then this epsilon corresponds to the error. And this y value, therefore, corresponds to the actual value. So this gives us a system of equations that we can write out as follows. So I have, for the first country, their equation would be 98 beta 1 plus 78 beta 2 plus the sum error term is giving us the actual value that we know for country 1 is 13. And for the other two countries whose data we have two more equations. So we have a system of three equations, and we can write this as a matrix equation as follows, where I organize the coefficients from matrix A times the beta 1, beta 2. So here's a vector of coefficients. We have two of them, one for each of the variables, plus a vector of error terms equals a vector of our actual values. And so the problem that we're considering now is how can I find the vector beta of coefficients, beta 1 and beta 2, so that we get the best linear model. So in other words, I want to find values for beta 1 and beta 2 so that our predictions are closest to the actual values. In other words, that we're minimizing the error in all of these predictions. And there are a couple of things that I should just mention. You might be wondering, why did I choose these two variables, literacy rate and life expectancy, and not other things? That's a really complicated question as far as what predictors should we include in our model. So the first thing we need to do is start experimenting with different models. So here's one such model that might work. And the second question you might be asking is, where did this formula come from? And there are all sorts of different types of regression models that we can use. But so that we can connect this back to the linear algebra concepts that we've been doing, that's why I chose this model initially. But what I want to leave us thinking about before we continue is, how can we find these betas? What is our notion of best linear model going to be? So how can we find these betas in a way that's going to minimize these errors? And that's what's going to lead to what are called least squared problems. And these types of problems are exactly what we're going to study next.